So it's a great pleasure for me to introduce the last speaker of this workshop, Professor André Nachbin. He's a full professor at IMPA. He works in applied mathematics, working in mathematical modeling, wave propagation, computational modeling, PDs. So André has many papers, and he also has formed several students, such as masters, PhD, and postdocs. So it's a great pleasure to have you here, André. Thank you very much for having accepted our invitation. So André, today we'll be talking about the wave-mediated Kuramoto-like synchronization of bouncing drops. Thank you, André. You can start.
Okay, thank you, Carlos. Thank you, all the organizers, Juan and everybody else. It's really a pleasure to be here. And as you will see, as all of you will see, this is going to be a quite different talk from the other ones. And it's a talk that I will show you. I will introduce it to a very new problem, which connects to many things. It's really a very new sort of playground where one can do modeling, write sort of PD systems to some extent for the first time, explore and discover new regimes, new solutions, and so on. So let me introduce you to this very nice story about bouncing droplets. So it started with Professor Yves Couder, who basically this around 2005, 2006, with his first papers. Well, he discovered this self-propelled object, which is a bouncing droplet dressed up with a wave field around it. And it's basically a wave particle object, a wave particle association, which was never sort of imagined to exist in classical mechanics. So it's very interesting from the applied hydrodynamic, it's fluids, modeling point of view, because we can write equations. As I said, it's a very fresh new playground for ideas and for exploring and for discovering things. And there is, as I will show you, a very big room, much room for theory. So what I'm going to be showing is modeling, so how to put equations together, have the problem nicely formulated. The problems are simple to phrase, as you will see, and I'm going to actually simplify some of them, but they're very difficult. I think the theory is very challenging, and the results are therefore the solutions, evidence of solutions of behavior are given through computational simulations. But it's really a playground for many types of skills in mathematics, including starting from PDs, wave equations, and dynamical systems. So here it is. It's, as I mentioned, an object never imagined to exist in classical mechanics, an object with wave and particle properties at the same time. So we had to do the PD modeling. We have actually from MIT, as I'll show you, our collaboration with MIT math department, we actually can have access to laboratory experiments. I'm going to show you in a second beautiful lab videos. So all the behavior is inferred by lab and numerical experiments, but lacking deeper mathematical theory. We can say what the answer should be, but there's no theory. So my talk today is really focused on the following. I'm going to have an oscillator, which is the droplet. I'll show you why is it an oscillator. And I'm going to have, therefore, a particle dynamics, which is wave mediated. There's a PDE for the wave, a wave equation that comes from potential theory, a dispersive wave equation that sort of governs the dynamics, the particle dynamics. So that's why it's a wave mediated particle dynamics, and many interesting things arise. So let's go to some beautiful videos that starts with the discovery of Yves Couder and results that then followed by the MIT group that was sort of recruited by Couder, and with John Bush from MIT visiting IMPA in 2012. That's how I got into the problem. So here are some beautiful videos of a bouncing droplet on the top left of silicon oil. So it's slightly viscous, has some surface tension, and this droplet levitates on the surface of the same fluid. Down here, then you see this droplet walking on the surface of the fluid. This is in Yves Couder's lab. It's millimetric, very small, but we can see it. So there's a bifurcation mechanism that actually has been shown through ODEs from the bouncing regime, where this droplet bounces, to the walking regime. It's a bifurcation where there's a parameter I'll show you in a second, that as you raise this parameter, the droplet destabilizes and starts walking, basically self-propagated by the wave field it generates. So it's a fantastic problem of a wave particle association, and this moves along. So this all started in this Nature paper by Kudev and collaborators. What is the underlying sort of fluids and actually even a differential equations mechanism for all this, so that we can start thinking about this? Well, the container, it's a small container of silicon oil. We see a cut of it here on the upper left. It is shaking at a given frequency, omega naught, usually 80 hertz, so 80 cycles per second. And that's enough not to allow the droplet to coalesce with the same fluid. There's a little thin air layer, which sort of it bounces through this air layer. Now, the wave that arises is actually known to some extent from a recipient that's shaking from a long time, and it's called Faraday waves. So these Faraday waves that you see in this square, and you see these standing, beautiful polygonal standing waves, was actually the mathematical analysis at first was done by Benjamin and Ursel, as you see in this yellow box, where they studied the stability. Basically, these are eigenmodes of the Laplacian that are triggered when you shake this container and you perturb it. No droplet, you just perturb it, and these standing waves arise, which are related to eigenmodes of the Laplacian if the cavity is square or if it's round. Well, here for the bouncing droplet, we are always below the Faraday threshold, the instability threshold. So if you shake it, you don't see anything. But as soon as you put the little droplet, as you see with the toothpick here on the bottom, the droplet, by pressing the free surface, it triggers locally the most unstable mode of the Laplacian. And that's the wave field. So as a first approximation for the circular sort of bath, it's a Bessel function, right? Okay, so this is the mechanism, this is the regime, and we're always going to be below the Faraday threshold. And the Faraday threshold, the bifurcation mechanism, is governed. If you see, as I put here, a sort of oscillatory gravity, this is going to appear in our differential equation. It's basically because we're in the reference frame of the container. So the gravity oscillates as we go up and down. And gamma, capital gamma, is the important parameter for bifurcations, for bouncing, walking, and so on. Basically, it's the strength of this sinusoidal vertical acceleration with a fixed, we're going to go work with a fixed frequency omega naught of 80 hertz. So this is the setup, the physical setup for the problem. I'll show you a little more physical experiments, and then I'll show you, tell in words how we deduce the PD and show you a simplified model. Okay, so Yves Couder, being a physicist, he said, well, I have this wave particle object. Let me reproduce Young's experiment by putting it through a double slit. And he sees many things similar to the experiment, like the interference pattern, the way it sort of, the uncertainty of the angles that it comes out, many, many things that are reported in this Physical Review Letters paper of 2006. So it's really fascinating. And this is, according to de Broglie, is called the pilot wave. And it really guides the droplet. You see, the droplet does not hit the boundary. It guides the droplet through one of the slits. Here we can actually see that the droplet goes through only one slit, but the wave goes through both slits, which is something that relates to quantum mechanics. There's a quantum mechanic analogy here, which I won't explore much, but it's really has been heavily explored in Couder's and John Bush's work. I'll give you a reference in just a second in terms of a review paper. And this really is something that reminds us from Young's experiment. Okay, so now, this is a first, I think, that has a mathematical appeal, which it's not really resolved, but it's really a beautiful thing, relates with a little bit with quantum mechanics and the quantum analog, but we can just think in terms of classical mechanics. We have this particle going around in a circular corral, right? It is confined to this region with the dashed line. You see that this little particle is moving back and forth. This video is strobed in the sense that you don't see the droplet jumping. It's always at the same height. So you see a little bit like a particle zipping around this container. It's doing, actually can do this sort of irregular orbit that we see here in white. But if you color code this orbit with a speed to see where the particle is spending, or the droplet is spending most of its time, we see this animation here, which is an animation from the laboratory. It's basically with real data doing this sort of random motion in the corral. So there's an ellipse in time, and the different speeds, and there's this colored spaghetti that at the end reveals some structure. So let me jump to the next slide where you're going to see the structure. The structure, as you see in the arrow, is these rings. And if they do, actually in this paper, the Paris and the MIT group together, if you do a rendering of where the droplet is spending more and less time, where it has more speed, it spends less time. So therefore, if you do this sort of experimental PDF, sort of probability distribution of where to find the droplet, it has a wave-like, so it looks like a wave function, a wave-like character that actually has a pattern. If you look here, looking absolute value, if you look here on the bottom right, that looks like the pattern of the most unstable eigenmode of the Laplacian, which is the Bessel function. So there's all these conjectures that, right, this, as we see in the blue box here, that there's a wave-like statistical pattern that emerges, right? If one waits long in time, so for a trajectory of sufficient length, and it has the cavity's most unstable, it looks like the cavity's most unstable mode. So here we see that there's this sort of a statement of ergodicity. If you wait long enough, the invariant measure surfaces, and basically this is what this rendering shows. So what are the mechanisms for this to arise? It's not fully understood. So as I said, many problems are posed and many questions have a sort of a partial answer or an evidence of the answer, and it demands for more theory. So here is a recent review paper by John Bush and a former student, Anand Oza, and it mentions a lot of the experiments and some of the sort of partial theory that exists, many models to address the certain theories. Some are a little more amenable, for example, to get the bifurcation mechanism for the bouncer to walking, gets the proper speed, and all that. It's in this paper. Okay, the math modeling. I'm going to give you in just a few words how is the math modeling for the more complicated problem, and then I'm going to reduce it to a simpler problem and tell you why. So the math model goes with the following ingredients. And this is the paper that explains in detail what I'm going to say very briefly in words. Basically, we had John Bush from MIT visiting, Paul Milewski from Bath also visited, and all of us sort of advising at the same time Carlos Galeano, a student from IMPA who's now in his second postdoc in England at Birmingham. So what we did is the waves that the droplet generate are not that large amplitude, so you can use linear waves. So but the viscosity of the fluid is important. So we start with a 3D fluid, 2D waves, because surface waves, and with the linear Navier-Stokes equation, and following a paper by Diaz, Diachenko, and Zakharov, we sort of can deduce a weakly viscous potential theory. I'm going to show you a little bit about this theory in a simplified manner in just a second. So we basically modeled the droplets' horizontal dynamics and vertical dynamics, how it bounces. So it can bounce at its own will, but in free space. Okay, no boundaries. So we cannot do the slit or anything. So in free space. But we got many properties very similar to the laboratory, in particular laboratory access. We have the laboratory at the math department at MIT. And here at the bottom, I compare the wave field of a photograph from Couder's lab with the wave field that the numerical method generates. And they're very similar among other things that we tested. This is the 3D, 2D problem, which means 3D fluids in a box, 2D waves on the free surface, but no boundaries. Now I want to put boundaries, and I want to show you why, and some very interesting things appear connecting to other problems. Okay, so here's the system. So it was just a bit slow. So my system goes like this. I'm going to have a domain where I'm going to have several cavities, and eventually I'm going to put two droplets, and I'm going to trap them to these cavities. So from the fluid dynamics point of view, this is a 2D problem, right? The fluids is in these cavities, two droplets on the top, and I need to generate waves as these droplets are bouncing. Basically, the droplets, the dynamics of the droplets is the position at where they are and the pressure they're exerting on the free surface to generate waves. Well, the weakly viscous potential theory is basically this system of equations that comes from potential theory. Phi is the velocity potential, eta is the wave elevation, and we have, let's look at the left here. In yellow, the viscous term that comes from the weakly viscous approximation. It's an asymptotic theory from Navier-Stokes all the way up to the free boundary conditions. Then we have the surface tension term in green, sigma, which is a little bit like this elastic bed that makes the droplet bounce and jump. In red, we have two terms in the bottom, each one for the pressure term exerted by the droplet as it presses the surface. Remember that it does not sink because there's a thin air layer. And finally, we have, and actually let me say it's centered at x1 next to the position of the droplets. I'm going to show you in just a second the system for the position of the droplets, the evolution of the droplets. This is the wave system that sort of guides the droplet. And the more complicated term in our system is a non-local term, a Fourier integral operator, which is here in blue, which is a Dirichlet to Neumann operator. This is very important to make this problem being able to be dealt with in the computer in a reasonable amount of time, because it's able for us to analytically reduce the problem to the free surface with high precision. Because in the Dirichlet to Neumann operator, we have information that the field, that the potential phi is harmonic. It satisfies the Neumann condition in this complicated non-smooth bottom, right? The bottom of the cavities. And it basically, I give it to the operator the Dirichlet condition, and it returns the Neumann condition. So here on the bottom, we have the expression. This is basically the Dirichlet to Neumann map in our canonical domain. So what do we do? The true domain is very complicated. Here in the top, we have a domain with two cavities. And the way to deal with this Dirichlet to Neumann operator, to construct it numerically, is to first do a conformal mapping to this strip here that you see on the right. On the strip, it's a very easy exercise to do the Dirichlet to Neumann map. Basically, you do it by put a Fourier mode on the top, do separation of variables, do the harmonic extension to the strip, and integrate. Here we have this Fourier integral operator here in the bottom, where the symbol is k tangent of k. It's very simple to be done in the canonical domain. But then using the conformal mapping, we are able to map back to the physical domain, which is the Dirichlet to Neumann map in Z, which I wrote here dt and Z, and where this capital M is basically the square root of the Jacobian of the conformal map evaluated on the free surface. Okay, this you see it in the papers. Here it's just words, but that's how we construct the Dirichlet to Neumann map. And since it's a Fourier integral operator, has a complicated symbol, doesn't matter. With an FFT numerically, it's really not a big deal. Okay, so we see that there's the Fourier mode gets highly distorted. As you can see, the grid with the curvilinear orthogonal coordinates that comes from the canonical domain gets highly stretched and compressed. We're able to deal with this numerically with some tricks and so on, but we're good. And so for those who are interested, there's these two papers. This one of the tunneling, I'll talk a little bit about tunneling at the very end. We explain how we do this conformal mapping, and actually on the side, we have with another student, I did this 3D Dirichlet to Neumann operator construction numerically for a 3D problem where we cannot use conformal mapping, right? We cannot use complex variables, but with a highly corrugated bottom, we're able to compute, and it works very well, the Dirichlet to Neumann, this pseudo-differential operator, the local pseudo, in 3D. Okay, all right. So now the equations for the droplets. The equations for the droplets are here. It's basically Newton's law. So we have mass times acceleration for one of the droplets. Let's see x1. The CF is a damping term because of friction of the droplet when it gets close to the free surface. So C is a bit of a friction constant, and the F of t that appears both places has information of surface tension and other things. So collapse there, and it changes in time. And the right term has actually the wave elevation, the slope of the wave elevation, eta x, and tells you how fast this pilot wave is going to be guiding our droplet in 1D. It's a little bit like a surfer. If you're high up on the wave, you move faster. If you're more near the trough, you move slower. So this is the ODE for the droplet dynamics in one dimension on the free surface, and it's connected to a PDE for generating waves depending on the droplet's bounds. So it's very complicated. There's a spirit of a free boundary problem because the feedback between the two systems, the ODE system and the PDE system, is highly nonlinear in the sense that we don't know, for example, in the next step, when the droplets are going to press the free surface and generate waves, and therefore we don't know exactly how the waves are going to be generated and are going to guide this droplet. Okay, so this is very complicated. Plus, the fact, as you see, I'm indicating here with this indicator function time, is that when the droplet is flying, all these terms are switched off. So we have discontinuous terms in the OD system and in the PD system. The pressure term switches off, and the forcing terms of the OD switches off. I mean, in the damping one also switches off. In the previous model, the droplet had the free will to bounce whenever it wanted. In our problem, in this problem, reduced problem to 1D, we actually decided that, okay, the droplet's going to have a period for jumping, and the contact time, which is not really contact, but the pressing time, is basically just a fraction, okay, 1/4 of the total Faraday period, which is the period of the wave and so on. These are more details. I don't want to get into these details. I want to tell you the whole story of this new problem and how it connects with actually known facts, which is very interesting in my opinion. I hope some of you or most of you agree as we go along. So this system is very complicated. It doesn't look that complicated because of the OD. Well, the wave equation is complicated, and it has this free boundary spirit, which makes it the problem very nonlinear. Okay, let me show you what happens in this scenario. I'm going to start so that we can I can convey ideas with one cavity, one droplet. Then I'm going to go to two droplets and many cavities, and you'll see many problems that already exist, in particular Kuramoto's model, as I mentioned in the title. So scientific computing to infer properties of this wave-mediated nonlinear oscillator dynamics. I'm going to tell you why oscillator. Okay, so here is explain to why an oscillator. I have one cavity. I have a droplet on the free surface, this little black dot. Okay, this picture is in time, the evolution in time of the droplet in one cavity, and as it is guided by the wave it generates. So in the beginning, it's quiescent. There's no waves. It starts bouncing, and it generates waves at every bounce. And in this case, in a small cavity and so on, it generates this beautiful wave pattern, and the droplet oscillates a bit like when I saw this for the first time. I said, well, it doesn't go to the boundaries where it's shallow. I didn't mention this, but the droplet doesn't like to walk on shallow regions, and it's good to have these shallow regions to avoid reflections and so on from the walls of the container. The droplet does not go to the boundaries. It stays oscillating in the middle and looks very much like a harmonic oscillator to some extent, right? So the first thing to note that's interesting is that look at the equation here for the droplet, for one droplet. We can now think, if this rings a bell of a harmonic oscillator, we see that the wave, eta, is playing the role of the potential, right, of a harmonic oscillator. But now the complication is that the potential varies in time, and the potential is not predetermined. It's generated by the particle. So that's where much of the complexity and richness of the problem comes from. Okay, so this is in time. We're going to see this type of graphs many times, and I'm also going to show to you this dynamics that looks like a harmonic oscillator in phase space, because then we can see cycles, right? If we had a harmonic oscillator, we would see cycles. So let's talk a little more about this. So here's the harmonic oscillator, right? So the usual harmonic oscillator, undergraduate, dV dx would be the harmonic oscillator if it was basically kx squared over 2, the parabola, with no time. But actually I can add some time to this parabola, which is if I shake it back and forth, I'm basically having a periodic forcing, right? Here you see in the bottom this rocking potential, a periodic force, and I get the mass spring, damped mass spring, force periodically, and you can have resonance or not, whatever. Now, this wave pattern that we see for our droplet looks pretty much like a sine that's just sloshing, right? A sine going back and forth, and the droplet moving on top of it. So this reminds us a little bit of the equation for the pendulum to some extent, if the wave is playing the role of the potential. So here, see, is the nonlinearity. If the sloshing is mild and we expand the sign, we actually get a cubic term, and it looks like Duffin's equation. Duffin's equation can already have many complications, even right before if we talk about the nonlinear pendulum. It's a nonlinear spring. So the wave, the PDE, is actually generating, evolving the potential, and you can think of it as a spring if you like, or just some potential. And this is what makes this problem also very interesting. And therefore we have the wave-mediated nonlinear oscillator, which has many interesting properties, in particular when I put two droplets. It's really interesting. Okay, so let me show you here now two droplets. So I put now two droplets in the same cavity just to see what happens, right? This is not the size of the droplet. This is just the position of the droplet. I put them in an asymmetric fashion. They sort of adjust themselves in a symmetric way, right? And start oscillating. And I notice that they oscillate like this, as my hand is doing. When one goes in, the other one goes in. When one goes out, the other one goes out. So what I did is I reflected them. So I went to phase space to see cycles, and I reflected them so I can see if they're doing the same thing or not, because it looks like they're doing the same thing, but I'm not sure, to see if they're doing this, moving at the same time one way or the other, because they're actually doing like this. So I just multiply by -1 and I reflect. And I'm going to show you an animation for this, okay? So here it is. So the animation started. I froze it for you because I want to mention to you. These spikes are exactly when the droplet lands on the wave and gets accelerated and decelerated. So at some points, actually, I'm going to remove the spikes from the orbit, but doesn't matter. And look what happens. The droplets start doing some sort of orbits, some cycles, start moving in, because they're sort of feeling the wave field that the PDEs are generating, okay, as they bounce. And eventually, here, as I showed you, they're already in two more or less limit cycles, a blue one and a red one. And look what happens. Here they are, okay, off they go, and they're kind of talking to each other, we don't see here, through the wave field. That's why it's wave-mediated dynamics of two nonlinear oscillators. And now, look what happens. Something happens that they're right on top of each other, so they're synchronized, completely synchronized, and on the same new limit cycle. Look, they're generating the new limit cycle. Let me accelerate here because I don't want to spend too much time of this. There's a new limit cycle of this synchronized dynamic. And who's doing all the job is the wave field, is the PDE. So this rings a bell of something which is very famous, very interesting, which is Kuramoto's model. Now I got to this. So Kuramoto's model is a famous model. It's a dynamic, finite dimensional dynamical system that sort of has the oscillators can spontaneously synchronize. It started with Winfrey that had a more complicated model. Kuramoto came in and made a simplified model. And it's a phenomenological model for phase transition from incoherent to coherent state. Coherent means everybody's doing the same thing. And it's a limit cycle, basically phase dynamics. You forget about the cycle, it's just the angle, the phase that's being governed by this equation, non-linearly coupled by the sign, okay? There's this coupling matrix that's sometimes just a constant, which means all the oscillators talk to each other equally. There's these very nice 3 review papers. I leave it to you to explore in the future if you're interested. And here in the bottom, we see the Kuramoto oscillators in the case where on the right, they're fully synchronized. It's phase locking. There's a slight lag, but it doesn't matter. They're doing the same thing. On the middle, it's partially locked, partially synchronized. And on the left, it's not synchronized. It's basically, it's a mess, right? It's incoherent, okay? So I realized that the droplet was doing something similar with a model much more complicated. And you see here the oscillators are explicitly coupled by the sine function. In my model, in the droplet model, they're not. They're actually coupled by a PDE, right? I'll come back to this. And there's much analysis of current interest in this problem. I got this, for example, this paper by Jared Bronsky, a good friend, a brilliant mathematician, that basically has been working on this. And you see fully synchronous solutions and synchronization for the finite n Kuramoto model. Most of the proofs of when it phase locks, when it doesn't, so on, are for large n and going sort of a little bit statistical mechanics technology. And you can see here in the bottom that he says that actually this represents the first rigorous proof for phase transition in a finite n model with finite n, right? And to this date, at the very bottom, you see this finite n model is only partially understood. And this is a much simpler model than the one I am using, okay? Which I'll remind to you in just a second. Here it is. You see, X1, look at the left in the ODE system. X1 does not talk directly to X2 oscillators. And it's not a phase model. It's the positions, everything. They talk to each other through the wave, which is governed by the system of PDEs that we see on the bottom. So it's very complicated, this nonlinear dynamics and interaction between oscillators. So let's continue playing with two oscillators, and you're going to see it gets even richer. So Couder has this beautiful video here where he shows that actually two droplets, if they get sort of close together, they can interact and, for example, form an orbit. And in this paper, they show that actually, because of the wave field that decays because of viscosity and so on, the droplets, basically, if there are 3 Faraday waves apart, this is what you see in this colored graph here on the top, they don't really see each other. But I realized that in these cavities, there was something happening that I could maybe make these droplets more than 3 Faraday waves apart interact, because I was seeing, so let me show you this. So here it is. So I put these droplets into 2 cavities. They're trapped in these cavities. I put this deep cavity in the middle because it acts a little bit as an amplifier for the waves going back and forth. And you see this complicated pattern in time. It's 7 Faraday wavelengths apart, right? And I noticed that the droplets, before I did this, I noticed that, as I was playing, the droplets were interacting. So let me show it to you. So again, I'm going to reflect the droplets and let's see what they do in phase space, because in phase space, we can see cycles. They do this very intricate orbit. Now, it's not just a simple limit cycle. It's kind of a limit cycle. I don't really know the name to call this. It's kind of a stable orbit because they stay near this orbit. Very complicated with loops. And look what happens here in the bottom as I animate. Because they're going to move very fast, the diamond on the bottom is basically adding the position of the 2 droplets. And if the diamond does not move, that means they're synchronized, right? Okay. And on the right, you see the other 2 droplets doing their crazy dynamics on this orbit. So here they are. And here you see the spikes from the times that they feel the wave. And on the top, I remove the spikes so we get a clear version of this sort of stable orbit. So look, it's almost, no, it's not synchronized. Now it's basically synchronized. But overall, it's basically nearly synchronized all the time. And I said, wow, in a different cavity, and the limit cycles are much more complicated than the Kuramoto ones, which basically the limit cycles, you don't see it. You just see the phases as they're going in phase space. So I said, okay, I want to try to break my record, put these droplets even further apart. So I did this. I put the droplets now 13 waves apart. I had to put 2 cavities in the middle for reasons that I don't want to get into, but to make the communication, you can see I put a very big barrier in the middle, and it's almost erasing the wave field as you see in the middle. So the communication is a bit faint, but there it is there. Okay. And I said, oh, I want to see the Kuramoto synchronization. All right. This is beautiful. I love this. I got it for some regimes and I want to put them far apart. And I did not get the Kuramoto synchronization. So I was frustrated for a while. And let me show you what I got. So I got another orbit. I don't really understand what sort of gives the form of these orbits, but let me mention it too. Phase space here is 4-dimensional because I have 2 particles. So I'm projecting, right, each particle, and I look and I superimpose the phase space of each particle. So we get these pictures. So already the nice thing is that the reference orbit is the same for both of them. But now here, they don't synchronize. They're sort of in the neighborhood. So off they go. They're in the neighborhood of this crazy orbit, not, following close to them. Loops here, loops there, but they're never close to each other. And the phase is very complicated because it's not constant phase like you saw in the Kuramoto one. Basically, the phase accelerates, decelerates, accelerates, decelerates. It looks like two racers on a track that never gets one close to the other. So it disappointed me because it fails to sync. And I thought, what can I get here in terms of anything that looks that they're doing together? So I decided to do the following. I said, well, since in particular in quantum mechanics, everything is in the probabilistic sense, I said, okay, let me ask you the following question. If I were to look for these two droplets, these two particles in phase space, what is the probability that I would find it here or there or elsewhere? So I did a histogram, a three-dimensional histogram in phase space. So I put the grid boxes. I start binning where they're visiting these droplets and seeing, they don't synchronize, and try to see what happens if I bin them, if I look at them in a statistical manner. And to my surprise and to my joy, they were identical. So I call this statistical indistinguishability, or statistically coherent. I cannot make a difference between these two guys if I just do the histogram binning. They're the same. Here you can see the binning of the left and the right droplet. So right as they're going around the reference orbit, as I show here in the bottom. So I said, are they really talking to each other? Well, let me see. A easy way to answer that is that, okay, I'm going to repeat the simulation, removing one of the droplets, right? Because if they're not talking to each other, it's going to do the same thing. And when I do it, the histogram for the lonely droplet is completely different and much more simple. So indeed, there is this wave mediated in a highly non-local fashion, making the two droplets synchronize, not in the standard Kuramoto way, now in a more general way, which is statistically. They're basically synchronized to some extent, statistically speaking. If you look at this, they're the same. Okay, so I have many questions to ask and look. So as I mentioned to you in the beginning of the talk, this is basically a research guided through computations, getting answers, complicated theory, because the systems, as I said, they are discontinuous terms, complicated free boundary kind of flavor, and many questions we can make and give sort of the answer, evidence of the answer, but there's really no theory from dynamical systems point of view or whatever you want to try to use. So I'm close to finishing. So let me go to the next transparency. So here, there's a tunneling experiment, which is another paper where we try to see how could a droplet escape from one cavity to the other, right? And we see that actually, it's a non-local problem. It's a highly unpredictable problem. This graph here on the top shows you that the time of residence of a droplet, a single droplet in one cavity, is random, right? It's unpredictable. When it tunnels, that means it jumps it's able to overcome the barrier and go to the next cavity. It's also unpredictable. So we have a paper on this compared to the laboratory experiments of Couder. And actually what we're looking now, now it moves, now I went too fast, sorry. Or at least it's working. So a current study we're doing is that we can actually set up the cavity with people with MIT and France, set up the cavity so that we can observe metastability. What does that mean? It means that the droplet wants to stay, the level of energy in the two cavities on the right, say, are different. When I have just one droplet, this red line means that the other droplet is inactive. So it sort of goes to the right cavity and basically stays there more time and say tunnels and come back. It doesn't like the right cavity. It's a little bit like a metastability situation. Now, what is very interesting is a collective behavior that when we have actually two droplets, which is this skinny vertical graph you see on the right, is that when you have two droplets, actually they tunnel more often. So basically one droplet to some extent is helping the other, and there's this collective improvement behavior. So that's something we are currently looking at. In my next graph, so I can finish, hopefully it comes, here it is. Here you see something that looks like that oscillator I showed to you. And here is a simpler closed orbit in phase space. And actually now with Nathan Kutz at the University of Washington, right, we are basically looking at this problem through dynamic mode decomposition, looking at basically the essence of the dynamics, numerically speaking, for this sort of harmonic oscillator type dynamics, and trying to get sort of an effective model. And for this case, even though we have dissipation from the fluids and forcing from the shaking, there are situations where we sort of can balance the energy. The energy calculation for this model is very complicated. But since it looks like a harmonic oscillator, there's situations where you have this balance. And through the technology that Nathan has, and in collaboration also with the MIT group, we're hoping, let's see if we have success, to extract from this complicated dynamics, maybe an effective Hamiltonian. So this is more or less why I wanted to say, basically my 40 minutes are over. Here are some references for recent work for these droplets which are connected at a distance, the tunneling paper, and thank you very much for your attention.
Well, thank you, André, for the very nice lecture. So someone has questions or comments, you can open the microphone or write on the chat. Acho que tem uma pergunta, one question on the chat.
Let me check
Hernan.
it. Stability.
How justify?
Yeah, but stability, help me, stability in what sense? De que maneira, Hernan? Stability. Oh, how to justify tunneling. Oh, okay, I see here. How to just in the top. So how to justify tunneling? We don't understand, Hernan. We don't understand tunneling, right? In the sense, Yves Coudet had an experimental paper on tunneling that's called, you know, the unpredictable or with tunneling. It's not. I mean, we know that in this oscillation, there's a moment where the droplet picks up enough speed that's to overcome the barrier. But I mean, the essence of the mechanism, we don't understand tunneling. Eventually, we would love to get something which maybe is not impossible, something, if we get a sort of a Schrodinger type equation for this, for example, through the Hamiltonian and so on, then tunneling from the quantum mechanics is a probabilistic way of thinking about it. Here, from the fluid dynamic point of view, we know that the droplet needs certain conditions to overcome the barrier. But we don't understand. We just know, it just confirms the laboratory experiments that it is unpredictable, random, as I showed you in the very end. The time of residence in the cavity is random, but mathematically speaking, we don't understand. So, and the stability, your stability questions too, I don't know in what context you're asking. Let me see here at the bottom. So please just put another word here so I can see what you want, what you're curious about stability. But the tunneling question is a good one. How to justify tunneling? It's not understood.
Okay. Any other questions? So if no questions, we would like to thank again André for accepting our invitation for the very nice lecture. Thank you, André.
Okay, thank you.